Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and I'm super excited for this one. It is day 17 of our hashtag 30 Days of Code Challenge with Educative. This problem is interesting, so let's get into it.
Today's problem is all about greediness, dynamic updates, and choosing the right data structure for the job. Maximal score after applying K operations. This is the kind of problem where brute force technically works on small inputs until you hit a real test case and it absolutely doesn't. Let's build the optimal solution from the ground up. Here's the game. We're given a list of positive numbers. Every turn, you follow a specific sequence of operations. First, pick the largest number in the list. Second, add that number to your score. Third, replace that number with the ceiling of the value divided by 3. Then repeat. You do this exactly k times, and at the end, you return your total score. Think of it conceptually like this. A big number shrinks down over time, but keeps getting reused. It's like a recycling loop for points. The question is, how do you maximize your score over K operations? Let me state the problem more formally so we're precise about the inputs and operations. The input here is you're given an array called nums, which contains positive integers. You're also given an integer k, which is the number of operations you must perform. Each operation consists of 3 steps. First, identify the maximum value in nums. Second, add that value to your running score. Third, replace that maximum value with the ceiling of the value divided by 3. The ceiling function means you round up to the nearest integer. So ceiling of 10 divided by 3 is 4, not 3.33. And the goal here is to return the maximum possible score after performing exactly k operations. The key word here is maximum. You want the highest score possible, which means you always take the largest available number. Let's start with the most obvious naive solution. This is what your brain naturally wants to do. Loop k times. On each iteration, find the maximum value in nums. That's one O(n) scan. Add it to your score. Then find the index of that maximum value, that's another O(n) scan, and replace it with ceiling of value divided by 3. Then repeat. This approach is correct. It follows the rules exactly. But here's the problem. It's slow. Each iteration takes O(n) time because you're scanning the entire array twice, once to find the max and once to find its index. Over k operations, that's O of k times n total time. If k and n are both small, this is fine. But if k is 100,000 and n is 100,000, you're looking at 10 billion operations. And that will time out. Let me break down exactly why this naive approach collapses. The bottleneck is finding the maximum value every single time. The max function scans the entire array from start to finish, checking every element. That's O of n. And then nums.index of max underscore val does another full scan to find where the max value lives. That's another O of n operation. So every operation costs O of n time, and you're doing it k operations. That's a total of O of k times n. When k and n are both on the order of 10 to the 5th, which is a common constraint in medium LeetCode problems, your algorithm attempts 10 to the 10th operations. That's 10 billion, way beyond any reasonable time limit. We need a data structure that gives us fast get max and a fast insert new value. And that's where heaps comes in. Heaps are perfect for this problem. Here's why. A heap is a tree-based data structure that maintains a specific property. The largest element in a max heap, or smallest element in a min heap, is always at the root. This means you can extract the max or min in O of log n time, not O of n. And when you insert a new element, the heap automatically reorganizes itself to maintain the heap property. That insertion also takes O of log n time. So with a max heap, each operation becomes extract max in O of log n, insert the new value in O of log n, which is total per operation O of log n. Over k operations, that's O of k times log n, which is dramatically better than O of k times n. For k equals 100,000 and n equals 100,000, O of k log n is about 100,000 times 17, which is under 2 million operations. Totally feasible here. Here's a practical detail you need to know if you're coding this in Python. Python's built-in heapq module implements a min heap, not a max heap. A min heap keeps the smallest element at the root, not the largest. But we need a max heap. So how do we simulate a max heap using a min heap? The trick is simple. Store negative values. If you push negative x for every number x, then the smallest negative number represents the largest original number. For example, if your original numbers are 1, 10, and 3, you store -1, -10, and -3. The smallest value in the heap is -10, which corresponds to the largest original value of 10. When you pop from the heap, you get the most negative value, which you flip back to positive to get the actual max. This negative value trick is a common pattern in Python interviews. Here's the clean and optimal Python solution. Let me walk through this code line by line. First, we import heapq for heap operations and math for the ceiling function. We create a max heap by taking every number in nums, negating it, and storing it in a list called max_heap. Then we call heapify to turn that list into a valid heap structure. This takes O of n time. We initialize score to 0. Then we loop k times. On each iteration, we pop the smallest element from the heap, which is the most negative number. We negate it to get the actual maximum value. We add that value to score. Then we compute ceiling of value divided by 3, negate it, and push it back into the heap. At the end, we return score. This is short, efficient, and it uses exactly the right tools for the job. This solution is optimal, and here's why. First, you must perform k operations. There's no shortcut. The problem requires exactly k operations, so any solution must have at least O of k time. Second, each operation requires knowing the largest element in the collection. A heap gives you the fastest possible way to maintain that information dynamically. Extracting the max and inserting a new value both take O of log n time. Third, there's no data structure that does better than O of log n for dynamic max extraction and insertion. Arrays take O of n to find the max. Sorted arrays take O of n to insert. Heaps are the sweet spot. So the final runtime is O of n to build the heap plus O of k times log n for k operations. The total here is O of n plus k times log n. The space complexity is O of n for storing the heap. This is the best we can do asymptotically. You cannot improve on this without changing the problem. Let's walk through a concrete example so you can see exactly how this works. We have nums equals, from left to right in the array, we have 1, 10, and 3. And k equals 3. So first we create the max heap by negating values. The heap becomes -10, -3, and -1. Now we perform k equals 3 operations. Turn 1, we pop the smallest value from the heap, which is negative 10. Negate it to get 10. Add 10 to the score. The score is now 10. Compute ceiling of 10 divided by 3, which is 4. Negate it to get negative 4, and push negative 4 back into the heap. The heap is now negative 4, negative 3, negative 1. Turn 2. Pop negative 4. Negate to get 4. Add 4 to score. Score is now 14. Compute ceiling of 4 divided by 3, which is 2. Negate to get negative 2 and push negative 2. The heap is now negative 3, negative 2, negative 1. Turn 3. Pop negative 3. Negate to get 3. Add 3 to the score. The score is now 17. Compute ceiling of 3 divided by 3, which is 1. Negate to get negative 1 and push negative 1. The heap is now negative 2, negative 1, negative 1. We've completed k equals 3 operations, so the final score is 17. That's the answer. Let's talk about edge cases you need to handle. First, k is very large. If k is much larger than n, you'll be reusing the same elements many times as they keep shrinking. The heap handles this naturally. Second, nums has only one element. The heap still works. You extract the same element, shrink it, and reinsert it k times. Third, all values are identical. No special handling needed. The heap works the same way. Fourth, very large numbers. The ceiling division matters here. Ceiling of 100 divided by 3 is 34, not 33. Make sure you're using the ceiling function correctly. Fifth, k greater than the length of nums. You'll cycle through reduced values. Again, the heap handles this smoothly. The heap pattern is robust and handles all these edge cases without special conditional logic. Today's lessons are fundamental. First, greedy plus heap is a powerful combination. Many optimization problems involve repeatedly taking the largest or smallest element and updating dynamically. Heaps are built for this. Second, replacing repeated max finding with a heap is a major optimization. O of k times log n beats O of k times n every single time. Third, Python's min heap becomes a max heap by storing negative values. This is a standard interview trick. Fourth, efficiency is often about choosing the right data structure, not just writing clever code. The algorithm here is simple. The magic is using a heap instead of naive scans. Fifth, understanding complexity trade-offs is critical. Knowing when O of n per operation is slow and when O of log n is acceptable separates good solutions from great solutions.
And that's a wrap for day 17 of our hashtag 30 days of code challenge with Educative. If you like this video, like it down below, comment, share it with a friend, subscribe to our channel. We would love to have you and share future breakdowns of LeetCode problems. See you soon.